Welcome once again to Physics 142 Online. I'd like to work an example problem using the Doppler effect for a somewhat practical application here. In the statement of the problem you can see, imagine that police use an ultrasonic wave technology to catch speeding motorists. Actually, in real life, they use one that's based on radar frequencies, but just to keep it simple, we'll assume that these waves are sound waves. If an officer in a stationary car sends a 100 kilohertz wave toward an oncoming car, and the reflected wave is measured by the officer to have a frequency of 135 kilohertz, how fast is the car moving? And I didn't write it down in the problem statement, but we'll assume that the speed of sound, the speed of the waves, is the familiar value of 340 meters per second. So how do we set this problem up? Well, we realize that in this case, there's actually two kinds of Doppler shifts for us to consider. So let's draw a simple picture. Here's the officer, and the officer is going to send out waves toward an oncoming vehicle. And so the vehicle's speed relative to the officer is what we're trying to find, and I'm going to call that V car. That's the question. So what we're given is we're given the frequency of the pulses that are in this ultrasonic wave, and that's 100 kilohertz. And we're also told that the officer is stationary. Now the thing about this is we want to somehow connect the frequency of the incoming pulse to the frequency of the pulse that's reflected off the car and then received again over here where the officer is. And that actually involves two steps. The first step is we think of the officer as the source, which makes sense, and the car as the observer. And so I'll just draw that on here. We've got observer, and then we've got source. And the reason we do this is in the second part, we're going to take the waves that are reflected from the car going back to the officer, and the car in that second part will act like the source. The officer will then be the final observer. So let's do first things first. We know that when we have the Doppler effect, that we've got an equation f prime is equal to f, and then we know it always looks like v with VO in the numerator, and then v and vs in the denominator for the source and the observer speeds. V is the wave speed. And what we have to do is figure out which signs to put in. All right? And the important thing here is to remember that the general equation looks like this. The general equation has f prime is f, and then we have v plus or minus VO, and in the denominator we have v minus or plus vs. And the key is that the upper sign is used if the motion is toward, and the lower sign is used if the motion is away. So we'll apply that right here. In this case, we've got the source at rest. So V source is equal to 0 and leaves the problem. Here, the observer velocity is the car velocity because the car is the observer. The observer is moving toward the source, and therefore we use the upper sign, which is the plus sign. But I'm going to call this f prime 1 because in just a moment we're going to turn this around and use it to find the final frequency measured back by the officer. So what we have with this then is f prime v plus v car, and I'll use v sub c to keep that simple, over v. All right, that's our first equation, f prime 1. No, sorry. Let me get rid of those primes because this should just be the original f. Right, so good. F prime 1 right here is equal to f, the original frequency of 100 kilohertz, times this multiplicative factor. Now let's turn it around and realize that the final frequency that's given is the frequency that's received by the officer. And so what happens here, the car is still moving, but the reflected wave off of the car that now has this frequency, f1 prime, that's the frequency that the car would have received in the first part of the problem, and that frequency now is returning to the officer. And therefore, the car becomes the source, and the officer is the observer. So what we're trying to find, then, is f prime 2. We're trying to find an expression for that. We actually know, I can put that number in, we know what that number is, and that's 135 kilohertz. So I'll write that in, 135 kilohertz. But the initial frequency is the f1 prime that we calculated in the first part. So let me go ahead and write this down. f2 prime, that's the 135 kilohertz, is equal to the incoming frequency, right? The frequency that came reflected off the car, which I'm going to call now the f1 prime, and we'll substitute for that in a minute. And now we still have the familiar, right? V and then VO over V and VS, and we have to figure out what to do with these. Well, remember now the car is the source, so it's moving. So the source speed is the car speed. VO, the observer, is the police officer who's not moving. So that goes away. And since, again, the source is moving toward the observer, then we use the upper sign, which in this case is the minus sign. So then this just becomes f1 prime times V over V minus Vs. Okay? But Vs is the car. So let me go ahead and make that clear. f1 prime V over V minus V sub C. All right, what do we do now? We're going to take the f1 prime expression from the top equation right here and plug it in to the f1 prime in the bottom equation, which is now right here. So let's do that. Sub in for f1 prime. All right, when we do that, what do we get? We get that f2 prime, which is 135, we know that, is equal to f1 prime, which comes from up here. F times V plus V car over V, now multiplied by this term, V over V minus V car. And look what happens. We get some simplification because those two V terms drop out, and we get an equation that actually looks pretty simple. Right here. So let's take stock. We've got f2 prime is equal to f times this multiplicative factor. Now the V, remember, is 340. So we know V, we know f, that's 100 kilohertz. We know f2 prime, that's 135 kilohertz. And what we're trying to do now is solve for V sub C, right? That's the unknown. And I notice I made a little mistake. I'll fix it here. I should have put in V car here. I think I said that, but I just didn't write it down properly. So how do we do that? Well, we could take the f2 prime. Yeah, let's do that. So we take f2 prime over f equals V plus V car over V minus V car. And just to save ourselves a little bit of extra writing, we can plug in the values for this. We know that's 135 kilohertz over 100 kilohertz, or 1.35. That's easy enough. So we've got V plus V car, V minus V car is 1.35, cross multiply, right? We need to get the V car all by itself on one side of the equation. So we have V plus VC is 1.35 times V minus VC, right? Or 1.35 V minus 1.35 V sub C. So we'll collect the V sub C terms on one side of the equation and collect the V terms on the other side of the equation, right? So this will give, if I do this right, we'll have V sub C times 1 plus 1.35 on the left-hand side. And on the right-hand side, once I subtract V from both sides, we'll get V times 1.35 minus 1, like that. So V sub C, Well, we can easily get that number. This is 2.35. Here we've got 0.35. And so finally, V sub c equals V times 0.35 over 2.35. Like that. V is our 340 that we used from above. This is a simple ratio, and when we plug the numbers in, we get a value of just about 51 meters per second. A little bit over 100 miles an hour, maybe 120 miles an hour. So that's a reasonable value. It makes reasonable sense given the context of the problem. So let me just review the important points of using a Doppler effect here when you want to find how a reflected wave, how its frequency is shifted. All right, going back to the beginning, the officer who sent out the pulse, then the pulse would have been received by the car at this first Doppler shifted frequency because the car acted as a moving observer. And so we found that expression right here. Okay? Then we turned around and used that frequency as the emitted frequency for the reflected wave coming off of the moving car, which now acts as the source. And so we used a Doppler shift equation here where the frequency that we normally would have just called f, we now put in as f1 prime because it's the value that we got in the previous part of the problem. So once we figure out how to do that, we get an answer finally for the final Doppler shifted frequency, which was the 135, in terms of the initial frequency, which was 100. And then by simple algebra, we were able to solve for the velocity of the source. In this case, the velocity of the car. So this is how the officer would know whether or not to write a ticket. So there are various variations of this kind of problem. We could have had the same setup with both the source and the observer moving, which would have made things even a little bit more complicated. Or with the source moving and the observer at rest. In either case, we would still use this same two-step approach to figure out the relationship between the incident wave and the final wave received back at the place where the waves came from. I hope this is helpful, and I will see you in class.